Hello everyone, welcome to this video poster. I'm Ivano Basile from the University of Mons, and to begin with I would like to thank the organizers for giving me the opportunity to present my work. And this will be a brief overview of some recent results I've been working on, hopefully to appear soon on the archive, and it is about the interactions of brains in non-supersymmetric string models. So in the more familiar supersymmetric settings, the interactions of brains is usually quite simple. In particular, in the simplest case of two parallel flat stacks of brains separated by some distance, the brains exert no force on each other when supersymmetry is preserved. On the other hand, when supersymmetry is broken, all bets are off, and the resulting interaction potentials are quite complicated and usually cannot even be computed within a single framework that comprises all the possible regimes. And this is why here I will focus on two complementary regimes. One is what I will call the string amplitude regime, in which the two flat stacks of brains are parametrically light, and so the interaction potential can be computed within string perturbation theory. The complementary regime, on the other hand, is the probe regime, in which one of the stacks is parametrically heavy compared to the other, and the gravitational back reaction on the background cannot be neglected anymore. And so what happens is that the resulting dynamics is described within effective field theory by the light stack behaving as a probe moving in the space-time geometry sourced by the heavy stack. So these are the two complementary regimes that I will consider, and the models at stake, just to set the stage, are in particular two orientifold models that live in 10 dimensions, and they are respectively an orientifold projection of the type 2b string and of the type 0b string. So the former model starts from a supersymmetric configuration, and then the projection breaks supersymmetry by a suitable combination of onine plane and anti-denying brains. And such a combination actually is non-tachyonic. On the other hand, the latter model starts from a non-supersymmetric tachyonic configuration, but the orientifold projection removes the tachyon from the spectrum. The resulting models have a rich spectrum of brains that has been classified long ago. But for our purposes, what matters is that the charged brains comprise D1, D3, and D5, and in particular, D3 brains are only charged in the orientifold of the 0b model, and then all the other brains are uncharged. And this distinction is quite important, since the interactions between charged brains of equal dimension is actually subject to the electric repulsion on top of the gravitational attraction. And the weak gravity conjecture tells us that such configurations should lead to a repulsive interaction in order for the theory to be consistent. And so let me now focus more specifically on this case, the case of charged brains of equal dimensions. So this result I'm going to present is actually valid for all dimensions, but in the models at stake, the relevant brains are D1 brains, for which the space-time geometry sourced by the heavy stack is an ADS throat. For D3 brains in the 0b model, the result is slightly more complicated, but the qualitative effect is actually the same. So I'm going to present the simpler result here. And this formula tells us that the interaction potential between these two stacks takes a form that is quite reminiscent of the supersymmetric counterpart of this scenario, which is D3 branes in type 2b moving in the supersymmetric AdS5 times S5 route. But the crucial difference with respect to the supersymmetric case is that in these models, this V0 constant here in front of the charge to tension ratio is strictly larger than 1. And so as a result, you can think of this as the effective renormalized charge to tension ratio increasing with respect to the bare value, and the resulting interaction is actually repulsive for like charge branes. And thus, indeed, the Wigg-Gravity conjecture is satisfied, although in a very non-trivial fashion, through the interaction mediated by the supersymmetry breaking effects. So moving on to the uncharged case, or at least a case in which one of the two stacks is uncharged, so that the charge doesn't matter anymore when computing the interaction, there are a few cases that can be considered. So in particular, in the probe regime, the geometries that are under control are generated by DP branes, in which case one has the AdS throat that I discussed briefly before, in particular for D1 branes. And then there is the geometry sourced by D8 branes that was found long ago by Das and Rad. And so in both cases, one can study branes probing the respective geometries sourced by the heavy stacks, and the resulting potentials look quite different since they are expressed in terms of the respective coordinates in the geometries, which are completely different, and also describe a very different regime of physics. But what is to be compared is the qualitative character of the interactions, namely whether the branes end up attracting or repelling each other. So these interactions are to be compared with the corresponding string amplitude calculation, and in this case, insofar as one of the two stacks is uncharged, can be actually computed easily from a three-level string diagram for any P and Q, so for branes of any dimensions. And the result for large distances can be compared to the probe regime, and in particular here are the plots of the potentials experienced by DP branes probing the geometry sourced by D8 branes. And indeed, we find a qualitative agreement among all the various cases, and in particular for the cases described by these plots. For P less than 4, the interaction is repulsive, whereas from P larger than 4 it is attractive, matching the corresponding string amplitude result. So it is quite impressive that these interactions match qualitatively without supersymmetry, since there is nothing to prevent the qualitative character of the potential changing as we tune the various parameters, in particular the number of branes involved in the interaction. But this matching somehow suggests, alongside the realization of the Wigg-Gravity conjecture, that there is some deep physics going on in these models, and their consistency is realized in quite exotic and non-trivial ways. So this is what I wanted to say, and if you have any questions during the Zoom session, please feel free to ask. Thank you for listening.